In this video, we're going to look at how to balance redox reactions. So this is going to be different than what you guys are used to with balancing equations because now we have to deal with electron transfer as well. Now, as we go through this balancing redox, this is section 20.2 in your book, so you can definitely look through that. It takes you step by step, just like we're going to look at in this video. Or another helpful website is down here at the bottom, and I will actually post this on the class website as well. So if you need extra practice with balancing redox, take a look at this helpful website. And so as we look at balancing redox equations, it's important to remember that we have to balance the equations for both charge and number of moles. So when we balanced equations before, we just balanced for the law of conservation of mass. We just looked at the number of moles. Well, now, because electrons are being transferred, we also have to make sure that we balance the charge as well. Because when we balance the charge, this makes sure that the number of electrons that are being gained are also equal to the number of electrons being lost. So we're going to look at half reactions as we look at balancing redox equations. The oxidation and the reduction reactions are written and balanced separately, and we call these half reactions. So all they are is we take the oxidation portion, we write it down, that's the oxidation half reaction, and then we do the same thing with the reduction. And then we use these half reactions to balance a redox reaction, and you're going to hear it called the half reaction method. So if you look down at the bottom, notice that we have the tin 2 plus going to 4 plus, that's the oxidation portion, and then we have the reduction half reaction underneath it. So even though the oxidation and the reduction reactions take place simultaneously, right, you can't have one without the other, it's more convenient to consider them two separate processes because then it allows us to make sure that the number of electrons that are being lost are equal to the number of electrons being gained. So like I said in the last slide, we're going to be using the half reaction method to balance redox reactions. Now, redox reactions can occur in either acidic or basic solution, and it's really important to make sure that you note which solution it's occurring in because that's going to actually affect how we add H plus and OH minus. Now, these are going to be the steps for acidic solutions, and then I'll tell you what the only difference is if you're dealing with a basic solution. So the steps. First thing you do is assign oxidation numbers, because that allows you to figure out what is being oxidized and what is being reduced. Remember I said whenever you deal with redox, always assign oxidation numbers first. And then once you know what is oxidized and what is reduced, separate them into the oxidation half reaction and the reduction half reaction. And then what we have to do is we have to balance each half reaction. So the first thing that we do is we balance for moles. We have to go based on the law of conservation of mass. So we start by balancing elements other than H and O. Save H and O for the end. Then we balance oxygen by adding H2O. So as soon as you balance everything except for H and O, then deal with oxygen. So then you balance oxygen by adding H2O to the side with less oxygens, because this is how we're going to add the oxygen. Then we balance hydrogen by adding H plus to the side with less H's. So you use H2O to balance oxygens, you use H plus to balance hydrogens. And then you're going to balance both reactions for charge by adding electrons. So we only add electrons to the side with usually the greater positive charge because that allows us to bring it back down. We need to make sure that both sides are equal for charge. So we start by doing moles, then we deal with balancing by charge. And then what we have to do is we have to multiply by a common factor in order to get our electrons equal, because we have to make sure that the electrons lost equal the number of electrons gained. Think about this like Hess's law. We had to multiply in order to get everything to equal. Well, that's what we have to do, except with electrons. Then you add the two half reactions together, you cancel out anything that appears on both sides of the equation. So the electrons should cancel. That's the first thing that you need to make sure cancel. And then if there's anything else, if you have water on the left and on the right, you can cancel out anything that appears on both sides. Then make sure that the equation is balanced. So just go back and verify, make sure that it's balanced for moles or mass and charge. And then we're going to deal with neutralizing if it's basic. So we're going to save this step 7 for the end, but all this is doing is if it's basic, we have to go through neutralization. So we're going to go through an entire example together. This is going to be the worked example, so it lets you go step by step through the half reaction method. Now this graph is very useful because this is actually the step-by-step of what we need to do as we balance. And so what we're going to do is we're going to consider the reaction between permanganate and oxalate. So here is the reaction between permanganate and oxalate. We form Mn2+ and CO2. Okay, so the first thing that we have to do is we have to assign oxidation numbers. So we have to go through, assign oxidation numbers. Remember that oxygen is 2- unless it's with fluorine, and then manganese here, because this is -8 total, this would have to be +7 because we need it to equal -1. Okay, so we go through, we assign oxidation numbers. Since manganese goes from +7 to +2, it's being reduced, and then carbon is going from +3 in oxalate to +4 CO2. Okay, so that means that it's oxidized. So now we know what's being reduced and what's being oxidized, so we have to split it into the two half reactions. So we're going to look at the oxidation half reaction. So we have the oxalate ion going to CO2. So what we need to do first is we need to balance everything except for H and O. So we're going to start by balancing the carbons. So we have 2 on the left, 1 on the right. Okay, so to balance carbon, we just add a coefficient of 2. Okay, so we start by balancing atoms other than H and O, so we would balance it just like we would any equation. So now let's check oxygens. We have 4 and we have 4. So oxygens are actually balanced now as well, so we don't have to worry about adding any waters. But charge isn't balanced. It's -2 on the left and it's neutral on the right. Whenever you balance charge, you have to use electrons. So we have to add 2 electrons to the right-hand side to make sure that charge is equal, because now we have -2 on the left. We have -2 total on the right. Okay, so our oxidation half reaction is good. Now we need to look at the reduction half reaction. So we have manganese, we have 1 on each. So manganese is balanced. So now we need to balance the oxygens. We have 4 oxygens on the left, we have 0 on the right. So we have to add water to balance the oxygens. So that means that we need to add 4 waters to the right-hand side. Okay, now we have 4 oxygens on the left, 4 oxygens on the right. But now our hydrogens aren't balanced. So to balance the hydrogens, we have 8 here, so we need to add 8 H pluses to the left side, because now that's going to give us 8 H's on the left, 8 H's on the right. So now all of the atoms are balanced, but now we need to make sure that charge is balanced. So what we need to do is we just need to add up the charge. We have 8 plus and 1 minus. So total on the left side we have +7. On the right hand side we have +2. So we have +7 and +2. So to balance the charge we need to add 5 electrons to the left hand side, because what that's going to allow us to do is now on the left side we have 8 minus 6. So we have +2 on the left, +2 on the right. So now we're balanced for charge. So now we've balanced for the atoms other than H and O, we've balanced for O, we've balanced for H, and now we've also balanced for the charge. So now our reduction half reaction is done. So now what we need to do is we need to combine the half reactions. So we put them together. We have the oxalate, we have the permanganate. So then to get the same number of electrons, right, before we add these together, our number of electrons need to be the same. So what that means is we have 2 electrons in the first, 5 in the second. These numbers, think of how we can get them equal. Well, if we multiply the top one by 5 and the bottom one by 2, that means that we get 10 electrons for each. So we multiply the top one by 5, we get 5 oxalates, 10 CO2s, and 10 electrons. We multiply the bottom by 2, so you multiply all of your coefficients by 2. Now our electrons equal, and we can add them together. Okay, so when we add them together, right, this is what we get. We have 10 electrons on the left, we have 10 electrons on the right. So what we can do now is we can cancel anything that's on the same side. So 10 electrons, and then that's all that is the same on the left as on the right. Okay, so we can cancel them out, and then this is what we get for our balanced oxidation reduction reaction. Now you can verify the equation just by counting the atoms, making sure that we have equal number of atoms, and then also balance the charge. The charge is what's going to be the most important. So we have 16, and then we have minus 2, minus 10. So we have 16 minus 10, I believe. 16 minus 12, right? 2 and 10. So 16 minus 12 is plus 4. 2 plus 2, we have plus 4. All right, so our charge is balanced, our atoms are balanced. So this oxidation reduction reaction, both half reactions are good, and this entire thing is now balanced. So now the only thing that we have to look at is what happens if this is in basic solution. So if this reaction would have been in basic solution, all we need to do is neutralize the H plus that we added. That's the only difference. We're going to do everything else the same way. So start by balancing it just as if it occurred in acid. So you use water to balance the oxygens, H plus to balance the hydrogens, and then you have to add OH minus to both sides in order to neutralize the H plus. Because you can't just add it to one side, because then you are changing the mass. The mass is no longer balanced. So just like in algebra, if you add 2x to one side, you have to add 2x to the other. So then you're going to add hydroxide to each side in order to neutralize H plus. And then you're just going to create water in its place. And we're going to look at some examples in class of balancing in basic versus acidic solution. Then if you have water on both sides after you neutralize the H plus, you can just cancel them out just like you do in Hess's law, or just like we did when we combined the two half reactions together. So that's the only difference between balancing it in basic solution and acidic solution. And like I said, we're going to look at a lot of examples when we balance any type of redox reaction.